We welcome your questions. You can submit them to us via email questions@wll.com. And now, I'd like to introduce our presenter and guest speaker. Michael Violette is a professional engineer and is founder and CEO of Washington Laboratories. He has worked in compliance since 600 megahertz seemed like a high frequency, and has authored numerous articles and publications for and about the industry. He has expanded WLL's operation to Asia and co-founded American Certification Body, with operations in the U.S., EU, and Asia, providing certification services to the global market. And we have a treat today. Our guest speaker is Steve Ferguson of Compliance Direction, LLC. He has over 40 years of experience in testing and device evaluation. He has instructed in the area of testing methods for the past 20 or so years, focusing on EMC, product safety, and environmental test methods. His comprehensive knowledge of MIL Standard 461, MIL Standard 810, MIL Standard 704, 1275, and 1399, and CE marking requirements for commercial and industrial equipment provides the ability to discuss the many aspects associated with regulatory compliance. With a background operating test laboratories and manufacturing companies, designing products, developing test procedures, and performing tests, he has the experience to address a wide variety of regulatory compliance topics. He presents various courses on EMI, EMC compliance, including EMC for nuclear power facilities, architecture shielding, and MIL Standard 461 testing, presented online and at customer facilities. So, without further ado, let's turn our attention to fundamentals of MIL Standard with Mike Violette and later after Steve Ferguson. Hi, Mike.
Hi, Kim. Thank you for the introduction. And hello, audience. I hope everybody's well and enjoying the new year and the promises that it has. I'm pleased to be able to address you. I can see some of industry colleagues have joined us, so welcome any feedback as we go along. And I am pleased to have Steve join us. We worked together for several decades in the laboratory, and now he's hung his shingle out to help other companies achieve compliance. So, Steve, feel free to chime in if I'm getting off course in any of these things, because, as I told you before, I borrowed some of your materials to make this presentation. So let's go. So the latest and greatest, MIL Standard 461G. The current version is G, and the original 461 was released back in 1967, so almost 50 years ago. 50 years have gone by, and over that time, a tremendous amount of electronics development, of course. So that was a seminal year. It was a roll-up to our participation in a little adventure in Southeast Asia. So there's a lot of development, electronics, controls, communications, and other devices. So 461, the original release, was used to treat those devices to ascertain electromagnetic compatibility. And given the types of technologies at the time, tube radios and solid state was just coming into fore more and more. Analog modulation was the main source of modulation. Radars were being developed at a fast pace. So a lot of these test setups kind of have their roots in original electronics development. And some of them may even seem to be like a non sequitur for more modern digital type of equipment. But nonetheless, I think as everyone here in this little class knows, once a spec gets printed in, it's hard to remove or update things. But 461G was an update. It was released in 2015, and it added additional simulations of electromagnetic noise, including induced lightning, ESD or electrostatic discharge testing for personnel, which has been around the commercial industry for 30 years or better, but now it's part of the MIL Standard regimen. Deleted CS106, which is, again, one of those kind of heritage tests that now has been overtaken by events, I think, due to technology evolution. It also added the General Requirements Section 4, which talks about configuration management, test equipment, measurement methods, calibration, and threshold measurements. So I cut my teeth on 461B/C, where a lot of the test methods were not prescriptive. You had to kind of figure out what you're doing, and usually did like legacy type of test methods based on your best guess. But the evolution of 461, particularly starting with revision D, really started focusing on more prescriptive types of tests. And G is really a fantastic document that's come together over the years that has a lot of industry knowledge to take away some of the guesswork when you're doing the tests. So the document is organized into 6 sections here, and quite an extensive appendix, more than 100 pages of application guidance and application of methods. So shortly, or in short, there's 4 kinds of tests, basically. CE, conducted emissions, where we're measuring either current or voltage on wires. And there's 3 different flavors of CE testing, depending on frequency ranges and methods. RE, radiated emissions, this is measuring electromagnetic energy propagating from boxes and from wires, and there's 3 flavors of that, again, depending on the different frequency range and type of equipment. And then there's 10 flavors of conducted susceptibility. This is where we're squirting electrons into cables to determine the response of the cable to the induced simulated noise. And finally, RS, radiated susceptibility, and there's 3 flavors of that, depending on magnetic or electric field type of induced energy. So these tests represent a mix of continuous wave, modulated, transient, and pulse tests, and also intended to simulate the environment and to measure the effect of equipment on the environment so everything can operate in harmony. So the first drawing here is a general configuration. This is pulled right out of the standard, and some of the features here have a ground plane. This is very typical for MIL type of applications. The ground plane is bonded to the enclosure through a bond strap. You'll have LISNs, line impedance stabilization networks, on the incoming AC power source or DC power source, and then an array of cables where the cable spacing is defined pretty in detail there. And the whole idea is to standardize the way that the measurements are made. So if you get a result from lab A and you want to repeat a lab B, that you have maybe a good chance of getting the same results. And this is important because, you know, lab facilities change. There's different labs may have multiple facilities or multiple enclosures, and getting consistency, that's the name of the game here. So the table height is defined, and the amount of cable configuration is defined, again, to get that consistency. So in general, the ground plane, the ideal is to bond the ground plane to the enclosure with a very low resistance or low impedance connection, again, to stabilize the test environment. Having the ground straps are prescribed to be have a length to width ratio of at least 5:1, and this is intended to reduce the high frequency inductance of the strap so you can maintain a low impedance connection. Cable arrangements are prescribed 10 centimeters back, elevated by 5 centimeters above the ground plane, and expose at least 2 meters of cable to the antenna. And this is designed to get a reasonable amount of energy that you're detecting from an antenna, and you're also exposing a sufficient amount of the cable to couple when you're doing radiated susceptibility tests. So you consider a tailored configuration to match the actual, and so tailoring is an important concept in those standard testing. You have to understand the operating environment. You got to understand how the device is configured. And often when you're going into negotiations with a customer or a procurement agency, it's recommended that you keep tailoring in mind because you don't want to over-test or under-test. But getting that all worked out in the beginning can eliminate a lot of concerns during the actual test. So this is a setup showing the non-conductive type of bench. It has a small batted ground plane that's where the LISNs are bonded to the enclosure. So again, you got a prescribed amount of exposed cable and a certain table height, again, to get consistency in the results. So the configuration for a non-conductive setup is the same as the general configuration, except the ground plane is used to bond the lizards, and the cable routes are not above the ground plane. This is an example of a freestanding or a non-tabletop type of equipment. You can see the EUT, or equipment under test, on the left is a larger rack or something like that that wouldn't normally be installed on the plane. But again, the general configuration is the same: bonding the enclosure to the ground plane, having lizards mounted to the ground plane, and a certain amount of cable spacing to get that desired consistency. So the configuration for freestanding is the same as the general configuration, except tabletop cable routing. The vertical cable is not part of the 2 meters of exposed cable. So let's go back to that EUT, and there's a cable, the configuration coming down from the top of the EUT, a certain amount of distance depending on obviously the size and the cable layout. But you have, again, a minimum of 2 meters of exposed horizontal cable coming from off of the EUT. And that can be power cables or signal cables, matter of fact. Not shown here is you may have some support equipment could be installed in the enclosure during the test. Often the cables are run out through a bulkhead, which gives the opportunity to filter or shield the cables that go to a support equipment. So that's pretty important, because you could often have, and this has happened quite often for us, is that the support equipment becomes part of the test, and you may have emissions from the support equipment that are not attributable to the EUT. So often the support equipment, if possible, is routed outside of the enclosure, so you're not causing a disruption with the actual results from the equipment you're testing. So this again is similar to outdoor type of configuration. This would be outside of a enclosure. Not unknown. We do a fair amount of MIL type work in the open environment. A little trickier because you're dealing with ambience, and if you're doing radiated susceptibility type testing, you have concerns about interfering with other services. So this is not ideal, but it's often necessary because either the size of the equipment or the arrangement of the equipment, or other limitations perhaps on power or other services that the equipment may need to operate correctly. So this is, again, the trickiest part, I think, because you have to contend with ambient signals and make sure that what you're measuring is actually from the equipment, not from other sources. It takes a kind of a keen eye and I think a little bit of practice to get this right. So again, same as general configuration. We've got the cables routed on the cable. One of the things that you need to do when setting this thing up is verify the bonding of the ground plane to the enclosure. I mentioned that before. We try to get it below 2.5 milliohms. Section 4.382 has provisions for making that measurement. And you may need to get multiple connections in order to get that low impedance connection to the enclosure. You should record the measurement in the test report. Make sure that that's understood. Now, one of the things that was new in the 461G was talking about measuring of thresholds. Previously, the quantity was not defined. And when I talk about threshold measurements, I'm talking about if you have an immunity or susceptibility situation and you're failing at some level, the prescribed level, the recommended approach is to back the level down until you get a certain threshold so you can find out at what level the equipment might be failing. So this is a representative sort of graphic from a CS101 type of test. And Steve's going to talk about this, a new approach for CS101 after my presentation here. Looking forward to that. But here you have a target level, and perhaps you have some immunity or susceptibility indications at a particular frequency. And so what you do is you back down the drive level until the interference disappears, and that would be recorded in the test report. So also incorporated in 461G is a FFT type of receiver. This Previously, spectrum analyzers or EMI receivers were typically used to make emissions measurements. But with the advent of these broadband FFT receivers, this is now an approved or acceptable method. Now, I have not done any tests with an FFT receiver. Perhaps someone in the audience has a little bit more to say about that. But one of the benefits of it is that it allows a much faster type of test. Whereas in the typical EMI receiver or spectrum analyzer, you have a determine step intervals and make sure that you collect all the emissions measurements that are there. But some of these FFT analyzers have multi-tens of megahertz of bandwidth, so you can perform these tests with much speedier. If you are using an FFT receiver, you have to meet certain ANSI requirements. And then you have to be cognizant, although you're testing fast, your EUT cycle time. What am I talking about there? This is the actual operation of whatever the EUT is doing, and you have to make sure you're dwelling long enough in order to capture the emissions during a typical cycle time. So there's some cautions there as well. And that applies to using an EMI receiver or spectrum analyzer well. And these are the step rates and the measurement times that are prescribed. You can see that over the frequency range of 30 hertz to better than 1 gigahertz, we have different measurement or resolution bandwidths that are prescribed. And so these are required in the measurement. Those IF bandwidths or res bandwidths have to be those minimum sizes. You could always use a bigger one if you want, but it may or may not be to your advantage depending on your system noise and the characteristics of the emissions. Also here is the dwell time if you're doing a stepped or tuned measurement. So you have to make sure you're dwelling long enough to capture whatever energy there is in that frequency band. Also prescribed in the G are loading and connections, and it's necessary that you terminate all electrical and output interfaces in order to simulate the actual device installation. And if you have some kind of mechanical output, maybe a motor or something like that, or an actuator, you should take into account the mechanical loads as well while you're doing the evaluation. So go into some of the tests. CE 101, this is conducted emissions. It's a low frequency measurement. It starts at 30 hertz and goes up to 50K, I think. And so this is to determine very low frequency power line type harmonics, and essentially, as we're starting below the power frequency. You are allowed to apply some limits. If your current is more than 1 ampere, or greater than 3 amperes rather, you can relax the limit by 20 log of the actual current draw divided by 3. And this gives you a relaxation that is reasonable, because if if you're drawing more current from the power system, you shouldn't be penalized by having to suppress emissions that just not physically make any sense. So one of the things that we have when we set up our emissions testing, we have LISNs or line impedance stabilization networks in line. You have to be careful with the amount of current rating on those things. You have to be mindful of that. Make sure that you have the right LISN rating so you don't have unwanted voltage drops. Because in line with the LISN, there's an inductor right there. So you could, if you have a high current draw, actually drop the operating voltage. So be mindful of that. Again, the last bullet on the bottom there is consider tailoring. If you have a large current draw type of equipment that you should consider looking at the CE 101 and 102 range adjusted particularly if you're using an alternate LISN. Again, tailoring. For CE 102, which is a higher frequency measurement, you're looking at basically the range of switch mode power supply type of noise. And so you have to make sure you're doing calibration verification at those frequencies. For CE 106, the last of our CEs here, this is for transmitter harmonics. And what we're looking at there is the out-of-band spurious emissions from transmitters. One of the cautions here is you got to make sure that you have the right amount of dynamic range, number one, so you can measure at those high frequencies. And number two, make sure that you have facility to notch the fundamental so you're not artificially overdriving your spectrum analyzer or whatever you're doing here. So this particular two plots show an actual transmitter, and it's the harmonics which are artificial because the input to the spec an was overdriven. So using a notch filter to tune out much of the fundamental emissions is necessary to protect the input to the measurement system. CS101, conducted susceptibility. This is a low frequency susceptibility test, 30 hertz to 150. This is applied to the power mains, and basically what it simulates is dirty power, if you want to call it that, or perhaps harmonics from other users that are on the power mains that may be drawing excess current and causing harmonic distortion of the power leads. Now this one definitely goes back to kind of the old days, the old analog radios, where you're concerned about power sources getting into radio receivers and radio transmitters. So some of the cautions for CS101, less than 10 kilohertz. Maybe I'll let Steve pick up on this because he's going to present on CS101 in some detail. These are some of the test currents for CS114. So this is a higher frequency injection simulation, and it's basically simulating RF noise sources that may be coupled into power and signal cables from other radio transmitters, essentially, or other types of emission sources. And that's sort of swept out from 10K to 200 megahertz. And you have different test levels depending on the type of equipment, the installation. So this is a quick setup of the CS114 pre-test calibration. Here you're looking at a signal generator, probably need an amplifier, and you're injecting the signal into the equipment under test or the cable under test, and simultaneously you have a measurement probe to make sure that your drive levels are correct. And these are the two calibration verifications. So this is the actual test. So you have the equipment under test. You have certain distances where you have injection probes and monitor probes, and they're specified to be 5 centimeters away from the equipment at least. And here we have a modulation signal generator and a power amplifier. And in this case, we've got a directional coupler, so we can monitor the RF output or the amount of drive level that we're going in. And simultaneously, we have a spectrum analyzer measurement receiver, so we're detecting the amount of drive current going into the equipment under test. And again, you don't want to overtest, so you're always monitoring the amount of current that's going in there so you hit the target level. This is sort of the way the current couples into the equipment under test. The next conducted susceptibility test is a new one for 461G, lightning-induced transients. So again, it depends on the applicability or specified in the procurement documents. So if you're speccing this up, and we look at this very carefully because this testing type of testing is not it's pretty expensive, and so we look at safety critical parts and things that may not have to test them according to safety critical devices. Here are some of the waveforms that are specified by CS117. Again, these simulate lightning injections. So depending on the attachment point, you may have a simple transient exponential, double exponential, or depending on where you're injecting, you may end up simulating damped oscillatory type of waveform. So there's quite a few waveforms, and one that is similar to perhaps an EFT type of test, which is the one waveform on the bottom. Here's some of the test levels, the different waveforms. And you can see that some of them depend on, these are aircraft basically requirements. So depending on where the equipment is installed in the aircraft, you'll have different waveforms. CS118 is new to MIL, at least over the last 5 years. As I mentioned before, it's been a commercial spec for as long as I've been doing this kind of work. 802.11 or 801-2 was the first IEC spec that had personnel waveforms. So there is a particular type of discharge, and there is a particular type of calibrations that's required in order to make sure that you have the right voltage level at static level. You use an electrostatic voltmeter to check the tip voltage, and then you have a ESD target to make sure that the waveform has the right characteristics. Getting the radiated emissions test, RE102. This is applicable across the board pretty much. 10 kilohertz to 18 gigs is the specified frequency range. Pretty much every type of device that goes through the MIL procurement spec gets this testing done. And the whole idea is to minimize the amount of electric field that are emanating from cables and cases, and this is to minimize the interference to other radio services. We have to do horizontal and vertical polarities. You may have to do multiple faces. Again, this would be called out by the test plan. Again, a little bit of tailoring here. And depending on the frequency range, you may have to have different antenna positions. One of the things that occurs at the higher frequencies is the beam width of the particularly horn antennas starts to collapse as you go up in frequency. And so you have to make sure you understand how wide that beam width is so you fully illuminate or you fully measure all the faces of the equipment. So again, this would be called out in the test plan where you'd specify the actual antenna locations and how many faces you do. So that's just a real quick fundamentals. This subject could go for days and days, and I know some of our colleagues in the industry can speak quite a long time on these various types of tests, and Steve Ferguson has done that in various settings. So they're comprehensive. They've evolved over time. I don't know. Maybe somebody in the audience, is there an H in the works? I think the committee is always working on tweaking the regulations and having more complex environments simulated. And as our electronic environments start to get more complicated, the types of tests that we are looking at evolve over time. And again, I'll just underscore tailoring may be something that you want to consider or should consider when you're looking at a test program. So here's a couple of contact points here, and we're going to leave the questions to the end. So I'm going to ask Steve to take the ball and run with it. Steve, you should have the ball right now. But you're muted.
Could you bring up my slides and I'll go with that?
There it is.
Okay.
Are you able to advance? Can you advance?
By the way, Mike, I appreciate you allowing me to come in and speak today about this proposal. But I've noticed that a couple of things. By the way, you mentioned something about not being aware of Rev H. Rev H the committee has not met as of yet with that. Okay, there's not a schedule available for them to be meeting on bringing that up.
Yeah, just curious.
Okay, yeah, it's good. It was a good point. Also, I wanted to take a minute to bring a little bit more light to that bonding requirement that was added. You mentioned earlier, and like you said, we're targeting 2.5 milliohms, but the revision G is more focused on emulating the installation more than getting to a specific value for the equipment bonding. Now, the enclosure bonding to the ground plane, et cetera, is 2.5. But although they target low, the real focus is getting to what the installation calls out and verifying that you match the installation. They want to be able to test it in the environment they're going to install it. So a couple of little added things there that I was conscious of, Mike. Proposal. I've brought this forward because I want to start thinking about it. I've made a proposal happen to the committee, and they've not met. The reason I was aware of them not meeting on it yet. And I did get some feedback from a couple of industry reps for that, and it gave me some elements that I need to do to make it more thorough, shall we say, in the presentation to the committee. So I'm working on that, so I intend to put this proposal in with the follow-up and additional supporting evidence to do that. So with that, there we go. As Mike indicated, this conducted susceptibility, and it shouldn't exhibit a malfunction when we apply these things. If at a test voltage level if applied to the power terminals. It's considered compliant if the settings for a pre-calibrated power is applied without attaining the test voltage. So we're getting into this venture of two limits, a limitation on how much we try before we end up not making our test happen. And with that, there's a couple of limit curves. The power limit up in the upper left in dB microvolts is the test level. And we also have the power level in the lower right side of 80 watts at the low frequency and diminishes down to about 0.09 by the 150 kilohertz. But the power limitation is met when we're there and we dissipate that power, as shown on the chart, into a half ohm load. Voltage or current measurements are used to establish the power limit, where the power is Ohm's law kind of thing, 6.3 volts for 80 watts to get a voltage curve. Or for current, it'd be 12.6 amps to attain the 80 watts. So why do we limit? If the characteristic impedance is very low, less than a half ohm, then the current will be increased trying to produce that voltage. And we could go on indefinitely applying more and more power, except that power limitation stops us from going so crazy. This produces a lot of excess heating based on the I square R, adding heat to the primary power. So if we have a power trace on a circuit board going to the power supply, and it's not rated to handle 12 amps of 80 watts if the impedance was low at frequency, this could be a DC powered unit and has a 3 or 4 amp circuit. But when I go to higher frequencies, we could shorten the higher frequencies out and produce a significant amount of current, overheating those traces and things like that. I've had these things happen over and over again, where we burn traces built into the circuit board, wiring starts to smoke, things like that, when the wiring is underrated to handle the normal power, plus what we add to it through all this current that we could produce depending on the characteristic impedance. So calibration in 461G is here, showing that we develop a power coupled into the circuit. That coupling transformer has got a 2 ohm source, half ohm load impedance secondary. So we're matching the impedance for the half ohm. Now, that's where we adjust to the voltage that we saw measured with the oscilloscope and record what the settings were, what the voltmeter output of the power amplifier or the signal generator. And this is, the words say that. I'm not going to bore you with just rereading what we just discussed, but I put it there in case you want to follow up. On the proposed method, I'm saying I would like to get rid of that measurement on the primary side and go to a current measurement, and we'll get to why we're doing that. This allows the current to be validated to be the maximum, or the half ohm load has got a voltage, so I'm measuring both. And I'm looking at these signals for the oscilloscope to verify they are sinusoidal. And the reason for doing that is to kind of ensure that I'm not overdriving the power amplifier, causing a lot of distortion. So we're operating the power amplifier system in the linear region. So a good power amplifier tolerates that pretty good. But we've got quite a few that get spec'd into the laboratory that may not be so responsive. So we need to validate that on an as-needed basis. Plus, make sure nothing is deteriorated. And that's what these words basically say. It's right now in case you have the slide. Now, when it comes time to do the test, the current version shows that we're measuring the test voltage at the UT terminals, that what we're applying to the circuit. And the current path takes us from the coupling transformer into the UT, all the way back around to through the Lisons, the power source, back to the other side of the coupling transformer on the secondary. With that, there'll be feedback across to the power amplifier, and we'll see some of that in the voltmeter settings and how it affects the power amplifier performance. And basically, that's what these words are saying, to do that. Remember, we disconnect the safety ground so the oscilloscope terminals become live. So you can be cautious, especially if you're doing three-phase power, where you connect to one of the phase leads as the alternate line. So the idea is to test each phase lead. When it comes time to do the test, we couple the signal here, and the question comes up. Do we measure the signal source at the voltmeter, or do we measure it at the signal generator? A lot of laboratories simply set the power amplifier up during calibration, record what the generator says, and then play that back. They can end up overdriving the system depending on the UT performance, overtest significantly, and the voltmeter reading allows you to change the gain. So this question came up during a discussion a couple of years ago now, and we've been studying it a lot since. This voltage variance, the data shows that there's more than 60 dB variance here, with the variance changes in the power amplifier. Applying a calibrated power without voltage limit gets a severe overtest. It can be 30, 40 dB too much. And we end up burning out traces on the board from an overtest, and it wasn't a legitimate failure. So we cause a failure because we weren't controlling the test adequately. Other configurations were explored. With some associates in Turkey, we did a complete study on this, and that study is there. My associates there did all the legwork on it. I was just an advisory kind of person. But we published an article available at that link, the Compliance Direction website. You can come through my website with the blog and look at that article about it. It'll link to the interference technology standard. And what we saw in there is if we measured with the control at the signal generator, we ended up applying a voltage of set that level indicated by the green line. If I use the control measured at the power amplifier, I had the red line, which is a significant difference in this area. And this is saying we're not going to meet the test voltage because we're drawing too much current. And so we saw this of the same amplifier at two different measurement points. This is a significant variance, and we said that shouldn't be tolerated. So we need to get that away from us. And we looked at that pretty heavily. Like I said, the article has a complete study with several pages of the detail about that. So in the proposed configuration, I eliminate that problem because we're going to monitor the current flowing in the system. And the voltage at the terminals also. Remember, the oscilloscope has got the isolated ground. Now, the concept is here that I produce the current or the voltage, whichever comes first. Now, Mike mentioned earlier about the greater than 10 kilohertz, less than 10 kilohertz, where we had to determine where the voltage drops were. And they could be down here in the Lisons. The inductive reactance of the Lisons or power filtering associated with feeding the Lisons from its source could be an effect here. So the idea is if we meet the current, then the voltage drops are of no concern. If we fail to meet the current and fail to meet the voltage, it's telling us that the voltage drops are being somewhere else, and we need to remedy that to get to either one or the other. So this proposal takes that into consideration. Excuse me, I went the wrong way here. So the proposed method connects the system. Remember again, the oscilloscope's still got that safety disconnect. and we set the generator attaining the lesser of the applied current or the test voltage. And we scan the generator of range, maintaining that with the test in each phase lead, just like we would normally do, except now we have the current feedback to be a control point. The benefits are recording the signal source is not required because I'm going to measure the current. I just need to see that the waveform is sinusoidal. Measuring applied voltage and current provides all the necessary control. The primary side control measurements are not degraded by secondary to primary feedback, so my measurements are being handled on the load side in all cases. And compensations for the signal losses, listens, etc., are not required if the voltage or currents are attained, as I mentioned. We also show that 461G calls out a 3-second dwell per frequency step. Well, this test method I'm proposing the test method does apply interference current to the source. So I'm seeing where I see a circuit resonance that can support a high current or a high voltage, meaning a high impedance or a low impedance or a minima or a maxima on the curve. And the current plus the intentional current can produce these high current levels. So the dwell time, because it's a short duration event, may not be there long enough for us to see the damage that's occurring, an overcurrent event. Now, it could damage it instantly or pretty quick, but the heating effects may be just deteriorating the circuit. The wire is starting to smoke, so if that frequency was present as a real interference, it could be there longer than 3 seconds. So I'm proposing a procedure step to dwell for an extended period at frequencies where the current's being elevated. That gives us a chance to evaluate that. I believe I put in at least 2-minute dwell time at resonant frequencies producing a high current levels. So basically, we use the test voltage or circuit current. I'm proposing we use the current as a control measure. Apply the test voltage and use the current as a control measure. I did submit a proposal to the committee and got industry feedback on that from that and need to do that. Committee review is not currently scheduled. That's why I know that the F committee, Revision H committee is not being met yet. And will it be accepted? I don't know. It's to be determined. So with that, I think there's my contact if you do that. With that, I can turn this back to the host for any potential questions.
Well, thank you, Mike and Steve. And yes, we did receive a few questions, so I'll get started. The first question actually had 2 questions. One, are 3 meter RE results accepted, or is 10 meters required?
I tell you what, we'll tag team. I'll take these first 2, and then Steve can take the next, and we'll kind of go back and forth.
Sounds good.
So yeah, I should have noted that in the setup, the test distance is 1 meter.
All right. And the next, sorry.
So the lab, I'll just go ahead and read it, Cam. How's the lab certified for 461G? Well, certification for a lab is probably not the right term, but accreditation is the one that's used for laboratory approvals. So typically what occurs is an outside auditor comes in, an accreditation body is the name of the organization, and there's half a dozen that operate in the U.S. and internationally also. So the accreditation body would come in and do a review of your setups, your scopes, your procedure, your personnel, record keeping. It's quite an intense audit, and Kim knows all about that because she participates in the Washington Labs accreditation body scheme. So really, a lab would be accredited. Now, there's not like a registry per se for MIL type work. It's dissimilar from, say, the FCC database, which a test lab would be accredited and then listed with the FCC. So there's no database like that in the MIL world, but accreditation would be the appropriate approval route for a 461G lab.
All right. The next question was, what about cables coming from industrial environment regarding conducted emissions?
Mike, I think you wanted me to take that one?
Yeah, if you want to take a stab at it.
I'm assuming the question is more or less dealing with the external cables and how they get in and out of the system. The setups allow you to use a simulation of function here to generate cables with a specific length of cable associated with it. So we're simulating those things in the laboratory environment. So hopefully that addresses that particular question.
Thank you. The next question for CS 101, I am sure that it was maybe already addressed, but how do you deal with measuring on AC power lines? They have an idea of what could be done, but would like to see what you all think.
Mike,
I think
I'll grab
you.
that.
Go ahead. Yep.
The measurements in the presence of that high voltage is very difficult. And because you're looking at basically a 60 or 400 hertz power line, that's a very high voltage, 240, 480, 120, etc. And that's going to be present with a low-level signal. So it's always difficult to do that. So fundamentally, there are transducer options available for 120 or 240 volt that tends to mitigate some of that visual issue. But there are concerns regarding that, and my associates that I worked with on the original study are looking at that too. And it can be somewhat difficult. A new article is just got presented at the EMC Europe by that group regarding some of that, so it'll be appearing in the IEEE transactions list. And that's going to be one of the new generation things to look at that. But the difficulties there, so you're looking at variance in the amplitude or the modulation level only. So normally when I look at this manually, I will do a peak-to-peak excursion, convert that back into the equivalence RMS to measure the test voltage. It is a little bit disconcerting. Okay. Next.
All right, thank you. Next question regarding CS114. For three-phase power, do you test each phase individually? The requirements say to test the complete bundle and with returns and grounds removed, but nothing about individual phase. Your thoughts?
I got it, Mike. The three-phase power lines are tested together, not individually. The concept is that CS114 is simulated radiated field coupling onto cables. And normally three-phase power lines are routed together, so they're exposed simultaneously or a common mode event. If these phase leads were to be routed in installation at different areas, a differential mode or individual test could become appropriate. Okay.
Thank you. The next question, does the RE102 test start from 10 kilohertz or 2 megahertz?
I think there's two different starts. It depends on the point of installation, right, Steve?
Yeah, the helicopter goes down to 10 kilohertz, some shipboard activities. Whatever the limit curve starts, that's the start frequency for that particular application. So once you pick the appropriate limit, the curve tells you where the start frequency is.
Yeah, and then 461G is pretty good about laying out a table for different services and different points of installation, whether like a Navy above decks or below decks, submarine, have different. They take into account the different environments.
All right. The next question will be regarding CS117, how cable bundles tests are applied to power lines if two isolated power lines exist with their return paths underground nearby the EUT, applied to both positive and negative line bundles together, or applied only to positive lines, or to all types of combinations?
You know, I have not done a CS117 test myself, so I don't know.
The power lines are treated a little bit differently because you need to get the lisins involved here. And this exposure again, is like, how is it installed to determine whether you test the bundle, if they're tied together in the routing, or it's two separate bundles or individual bundles. But normally it's tested as a coupling event to the power line versus a direct conduction. So it tends to be a common mode on the power bundles, and they can vary based on their routings.
All right. How do MIL Standard 461 tests correlate with the EN IEC 61000-4-X test? How much, if any, overlap exists?
There's similarity, but the methods are quite different. The limits are quite different. In the commercial world, for example, on emissions, we have peak, quasi-peak, and average type of measurements for different types of emissions. Where in the MIL world, it's all peak. As far as the susceptibility and immunity, so in the commercial world, we say immunity. There is some similarities in the tests, but the tests are performed in different environments typically, and frequency ranges are different. So for example, there's a magnetic immunity test in MIL Standard 461 that doesn't appear in the same way, like this called RS-101, as in the commercial spec. It does overlap at a few frequencies, at the power frequencies, but the magnetic immunity test for the MIL is much, much broader, covers a lot more sources. We mentioned the measurement distance and the antenna distance. And in the commercial world, the test distances are typically for emissions at 3 and 10 meters, depending on the class of equipment, what you're testing. In the MIL world, they're all 1 meters. So there's some correspondence in the type of tests, but there's not enough correlation that you can compare one to the other too well.
All right. You mentioned the use of notch filters to overcome measurement overload. As far as I'm aware, the filter response of a notch filter is relatively narrowband. Modern frequency hopping transmitter techniques can operate over a much wider band than the notch filter. Is there any solution to notch out much broader bandwidth transmission?
We struggle with this sometimes, and so we have a variety of high pass and low pass type filters. For example, one of the most effective methods that we have for the higher frequency radiated measurements are to use waveguide filters. And basically, these are different size back-to-back waveguide coupling modes that have an extremely sharp cutoff. They're a high-pass type of design. And then we've got a variety of low-pass if you're trying to measure below a certain frequency and you're trying to suppress a higher frequency. So it's a challenge. And one of the things that occurs in the lab is that the frequencies are different for different types of operations. So we have to, number one, be very careful about not overloading our analyzers. And when I caution our guys, always start with a lot of attenuation and work your way back, particularly if you're not sure what you're going to be measuring. And then carefully quantify the filter or filter combinations so you take into account any attenuation that may be offered in band or out of band.
Okay. Will there be another webinar that focuses on the calibration and verification procedures for CE 102 and RE 102? There is not a lot of info in the standard regarding how to properly perform these measurements. That's a good one. Maybe we could put together.
Maybe I'll invite our honored guest speaker to do something.
All right.
Well, I think I would like to do that. That sounds like a reasonable thing to do. Mike, would you host such a presentation for me?
Be happy to. In fact, we had a session 2 of the MIL webinar that we're still forming up, so this is a perfect suggestion. A little deeper dive.
All right, seems good. Next one, power input for EUT is preferred shielded or unshielded?
I can answer that one real quick.
Yeah, go ahead.
It says no shielded cables, no shielded power cables. Done.
All right, thank you. What is the background to the addition of 4 kilohertz CSRS testing starting 461F Navy?
Mike, I got that.
Yeah, go ahead.
The 4 kilohertz is associated with shipboard activities because the power transfer systems of the ship have placed a common mode signal that does couple quite a distance on shipboard distribution. So the shipboard activities added the lower frequency common mode test for that.
Steve, I think you got the next one. It's about studying for the INRD certification.
Yep. Studying for the INRD certification. You can go forever studying for that. They have the practice exams and the study guides. Depending on which element you're looking for on the INRD certification, the engineering group has a particular set of study things. The MIL standard has a particular set of study things. But generally, you need to get a technician or engineer certification, and then you've got the add-on MIL standard part of that. So you certainly can do that. Some of the courses that I do are approved training courses for the MIL standard section that I've been doing. So the idea is it's there and studying anything and everything. When it comes time to do the test, if you think that you need all these reference materials, forget it. If you've got to research a question, you'll run out of time before you get them all researched in detail. Be comfortable with what you do, understand the concepts. It's not an overwhelming test. It's not bad. So it is thorough, I'll give you that. And if you've been doing this for a while and listening to webinars like you saw today and any of the others that I know Washington Labs presents a huge amount of things dealing with radios and you name it, and it's good knowledge base. Attending those web sessions is a great study tool.
Thank you. How to identify its common mode noise or differential mode noise?
Well, on AC power, you're often measuring a combination of that. You're measuring the line to ground voltage, but you may have differential mode mixed in there. There's a textbook, I think, by Clayton Paul that shows there's a filter network. I can't remember what it is. It's using ferrites and stuff to basically reject the common mode, and so you're looking at only the differential mode. I'd have to look that up. I don't know what the filter looks like offhand, but I know I saw it once upon a time.
Mike, to add a little bit to that, sometimes if you're experiencing this and it's dealing with cables, if you separate the wires and put one through the current probe in the reverse direction, they tend to cancel each other if they're differential. So if the level stays the same, it's common. If it deteriorates when you do that, it tends to indicate that's a differential signal. Just a little element of the test associated with that.
All right, gentlemen, we have a few more questions and we'll wrap it up. Regarding my CS 101 on AC power, why not look at using an oscilloscope with an FFT capability? This will give frequency selective voltage measurements. What are your thoughts on this?
Absolutely. It does a good job of doing that. Still, the feedback is difficult to get control that way, but it definitely lets you be able to look at that in the frequency domain and determine those. That works pretty good.
All right. Do you have a suggestion to decrease ambient electrical field noise for RS-103 tests for low and high frequencies?
Well, maybe he's referring to RE-102. I can't put ambient with RS-103 because that's a susceptibility test, and you're typically not concerned about the ambient because you're hitting it with such a high level that you would probably be overcoming any ambient signals. And that's just in general, this is why things are done in a shielded enclosure.
Why MIL Standard 461 deals with CS 103, 104, 105, 106, and RE 103?
Those are radio-specific elements, and they're just not accomplished on a large variety of equipment. There's a lot of information available about those tests through various reference materials and et cetera. But I know, Mike, you left those out because they're not a common test. It happens on a small percentage of the overall test, and this is a more of a high-level kind of webinar. So I'm sure that's why we didn't try to cover those, just a time consideration.
So I mentioned in the beginning, this could be a week-long course.
Yeah, when I teach it, it's a week-long course.
Yeah.
All right, I think I've asked all the questions that came in. I know someone had asked, will they receive the presentation? For all who have registered, and of course you guys who are on here now, will receive the recorded presentation along with the presentation slides. I usually take about 1 to 2 business days after the live webinar to get that prepared and get it together. So yes, you will receive it. And I believe, again, I think I asked all the questions. So with that said, again, I want to thank Mike and Steve for taking time out to enlighten us about fundamentals of MIL Standard. We are currently working on finalizing our 2021 webinar series with confirmed dates and times with the presenters. We also have a series of Road and Swart webinars in the works for this year. So if you haven't already done so, make sure you visit our website to subscribe to our Washington Labs Academy to receive updates. This is easily done by visiting WLL.com. You'll click on that training tab in the upper right corner and you'll fill in your information where you see sign up for updates. So on behalf of the Washington Labs Academy, I would like to thank you all for attending. I will now end this event. Please enjoy the rest of your day and most importantly, be safe. Thanks again, everyone.